Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about a self-controlled synchronous motor drive. Very specifically, we took the example of a load commutated synchronous motor drive. Now, in the load commutated synchronous motor drive, what we saw is that the synchronous motor is connected to a load side converter, and this is a CSI or a current source inverter. So, the synchronous motor is operated with a closed loop rotor position feedback. So, we have a position sensor which gave the feedback to control the load side converter. We also derived the expression for the commutation, the overlap angle. This is the overlap angle which can be evaluated from this expression. Mu is the overlap angle for the load side commutator, load side converter, and we also saw the closed loop speed control block diagram of this load commutated synchronous motor drive. One thing we should understand that this is a self controlled synchronous motor. So, this is a self controlled synchronous motor, and for that we have to have a position feedback or a feedback of the phase of the rotor. So, this frequency feedback basically gives the phase angle. So, we are able to control the load side converter using this kind of feedback. So, unless we have a feedback, we will not be able to control the synchronous motor drive in self control mode, because the synchronous motor always will remain in synchronism with the rotor. So, there has to be a synchronism between the stator and the rotor for a synchronous motor drive at all frequencies. Let us take the example of another type of motor which are called brushless DC motors. They are also synchronous motors, but they have an inherent closed loop position feedback. So, let us discuss about the brushless DC motor. So, we call this abbreviation as BLDCM or brushless DC motor. So, we will first take a very simple BLDC motor. We will talk about a low cost BLDC motor. BLDC stands for brushless DC motor. Now, what we have here, we have a motor with 3 stator windings. Let us say we have 3 stator windings, and these windings are energized by a power transistor. Each one is energized by a power transistor. So, we have 3 power transistors, and this is supplied from a DC supply. So, we have a DC supply here in the DC side, so each one is a power transistor here. So, we call this to be phase 1, phase 2 and phase 3, and each phase is connected or is shunted by a freewheeling diode. This is basically to freewheel the current when the transistor is switched off. So, we have 3 transistors T1, T2 and T3, and the DC side is VDC. So, if we see in a schematic fashion the construction of this kind of brushless DC motor, we will see that we have a rotor and we have 3 stator. stator winding, phase A or phase 1, phase 2 and phase 3. So, we call this to be phase 1 here, phase 2 and phase 3. And the rotor in this case is a permanent magnet rotor. So, we have a permanent magnet rotor here. So, rotor has permanent magnet. So, we have a distinct south pole and distinct north pole and distinct south pole. So, we have a north pole here and we have a south pole here. So, this is a permanent magnet rotor. And the stator is connected to 3 transistor, 3 power transistor in the following fashion. So, what we have to do here, this is a closed loop drive. So, we have to have a position sensor. So, we connect a position sensor to the rotor. So, we sense the rotor position and we trigger the transistors T1, T2 and T3, base drive for T1, T2 and T3. Now, to understand this, we will take the example of a position sensor which is a encoder. So, we connect an encoder to the rotor. A rotor has a permanent magnet field and let us say we assume there is a 2 pole in the field, one north pole and one south pole. Let us see the rotor structure of this brushless DC motor. In the rotor, we have the structure here that let us say this is, we are dividing into 60-degree segments and here we have a photocoupler PC1 and we have a photocoupler here that is PC2 and we have a photocoupler here that is PC3 and we have a magnet which is placed in the rotor and the magnet has a north pole and has a south pole. So, we have a north pole here and we have a south pole here. So, the rotor has a magnet. So, this is the rotor. Rotor with encoder disc. So, this region of the encoder is opaque. So, the region which is marked in hash is a opaque region. So, we have 2 photocoupler PC1, PC2, PC3. Photocoupler means at one side we have a light emitting diode, on the other side we have a phototransistor. When there is transparent region, the light passes through and the phototransistor receives the signal and gives a signal that is equal to 1. And if the opaque region comes, the light is obstructed, the photocoupler output becomes equal to 0. So, we have 3 photocoupler PC1, PC2 and PC3 and the various phases are aligned like this. Let us say this is our phase A or phase 1 which is aligned here and we have phase 2 which is aligned here and we have phase 3 which is aligned here. So, this is phase 1 and we have phase 2 which is here and we have phase 3 which is at this point. Now, when a phase is energized, when we energize a phase, the phase creates a south pole and south pole attracts the north pole. So, let us say we energize phase 1. So, when we energize phase 1, the current will flow through the phase 1 and through the transistor it goes back to the supply. So, this is the flow of the current. So, when phase 1 is energized, there is a south pole which is created here. So, the south pole which is created here will attract the north pole. So, the magnet, the rotor magnet will move and when the rotor magnet will move, the disc is fixed to the rotor and also the magnet is also fixed to the rotor. So, when the rotor rotates, the disc also rotates. Disc has got some opaque region and the opaque region will also move, and the photocoupler which was getting a 0 signal or which was outputting a 0 signal will give us a 1 signal. So, in this case, once we create a south pole here, north pole will be attracted and the rotor will try to move towards the south pole. So, the motion will be clockwise. So, let us see what is the arrangement for clockwise rotation. So, we want to have clockwise rotation. For clockwise rotation, what we have to do here? Right now, what happens? Right now, PC1 is getting a signal that is equal to 1, because this is in the transparent region. So, this region is transparent and this region is the opaque region. So, when the region is opaque, the photocoupler output becomes equal to 0. So, PC1 is getting right now PC1 output is 1, PC2 output is 0, PC3 output is 0. So, PC1 is in the transparent region. So, the light from one side is received by the phototransistor and the output of the transistor is 1, and other two light sources are obstructed by the opaque medium. So, the outputs of PC2 and PC3 are 0. So, under this condition PC1 feeds the base of the transistor, that is T1. So, for the clockwise rotation, PC1 feeds T1 which is connected to phase 1. So, phase 1 is energized. So, when the phase 1 is energized, we see that the rotor north pole will be attracted towards the south pole and the rotor will move in the clockwise direction. And after that, after some time, PC1 will be covered and PC2 will be uncovered. So, when the PC2 is uncovered, the magnet would be along this position, the magnet would lie along this position. This will be the north pole and this will be the south pole. So, under that condition, PC2 has to be energized by phase 2 has to be energized by PC2. So, PC2 has to feed transistor 2 which is connected to phase 2, and similarly after some time PC3 will be on, PC3 feeds T3 which is the phase 3. So, in this case there is a continuous rotation, because the encoder gives the signal at any point of time one of the photocoupler is 1. So, the photocoupler are connected to the base of the transistors and the corresponding transistor turns on and this is a continuous rotation. Now, why it is called a brushless DC motor? Because there is no brush and the rotation is being achieved, we have a DC input. Without a brush, the input being DC, the motor behaves like a brushless DC motor, and the commutation is achieved electronically. The commutation is achieved by the encoder as well as the 3 power transistors T1, T2 and T3. So, here the windings are phase 1, phase 2 and phase 3 which are energized by T1, T2 and T3, and the input is VDC, and since we do not have any brush here, there is a continuous rotation in the clockwise direction, we call this to be a brushless DC motor or BLDC motor. Now, what about anti-clockwise rotation? Say for example, we would like to have counterclockwise rotation, clockwise rotation. So, if we have to rotate the motor in the counterclockwise direction, it has to the connection has to be changed. So, the connections would be the following. Now, we would like the motor to rotate in counterclockwise rotation. So, this will be the rotation here. Now, if we have a north pole here, the north pole should be attracted to the south pole, which should be below the phase 3. So, here we should have a south pole. So, when we have a south pole here, the north pole will be attracted towards the south pole, and the motor will rotate in the counterclockwise direction. So, here PC3 or PC1 has to feed phase 3 or T3 transistor. So, T3 transistor has to be energized, which will be energizing the phase 3. So, in this case PC1 feeds T3, which is connected to phase 3. Similarly, we can see here that PC2 has to feed T1, which is the phase 1, and PC3 has to feed T2 or phase 2. So, for counterclockwise rotation, we have to change the connection. The connection has to be PC1 is connected to the base of transistor 3, that is this one. PC2 has to be connected to the transistor, the base of the transistor T1. PC3 has to feed the base of the transistor T2. So, this is a low cost motor. So, what is the application here? There is no brass, the rotor is a permanent magnet, the stators are concentric winding. The stators are not distributed winding, stators are concentric winding. These motors are very popular in computer fans. In computer power supply, we have a switch mode power supply, we use a fan, that fan is a brushless DC motor. There is no AC there, we are applying a DC to the motor rotates for years without getting damaged, because there is no brass. Since there is no brass, there is no maintenance. Similarly, the CPU fan is also a brushless DC motor. So, this fan or the application of this are fans for computer power supply, computer power supply. Now, if we notice one thing, that the torque is being produced here, but the torque here is pulsating in nature. So, if we see here that the torque is proportional to the angle between the two magnets. One is a permanent magnet which is produced, which is the rotor, which is the north pole and south pole. Another magnet is the electromagnet produced by the phase windings. The phase windings are, we have the winding here, we have the winding here, and we have the 3 windings in this case, as we have seen here, phase 1, phase 2 and phase 3. This is, let us say, phase 1, phase 2 and phase 3. The principle is that whenever we energize a winding, a south pole is created under that winding and the south pole attracts the north pole. The magnets can rotate either in clockwise rotation, or if we excite this winding, the south pole is created here, the motor may rotate in the counterclockwise rotation. Now, in this case, the angle between the two magnets change between 120 to 0, because if you see this encoder, the encoder, this angle is 120, this angle is 120 degree. So, the encoder photocoupler gets a high signal for 120 degree. So, the variation of delta in this case happens between 0 to 120. So, the torque in this case varies like this. So, if you plot the torque waveform here, so this is our theta is the rotational angle. So, the rotation happens like this. So, as it rotates, so basically delta is 120 here and this goes to 0. So, the torque will change in the following fashion, a sine wave. So, this is the torque versus theta, theta is the rotor angle, and what we see here that this is the torque that we get, the output of the motor, and since this is a positive torque, the average of this value is positive. So, if you want to calculate the average value, the average is positive here, T average is positive. So, we have a positive rotation either in clockwise or on anti-clockwise direction, but there is a torque pulsation. The torque pulsation does not matter for a fan, because fan is a low performance application. There will be little bit of noise, but for a drive application which require high performance, the torque pulsation results in vibration and noise. So, we will see a better brushless DC motor, where the low cost brushless DC motor is replaced by a trapezoidally excited permanent magnet AC motor. So, let us see a trapezoidally excited permanent magnet AC motor. So, we will be discussing right now the trapezoidal permanent magnet AC motor. Now, in this case, let us see the constructional feature here. We have a rotor, we also have a stator. The stator has got this structure here. So, we have we divide this into 60-degree intervals, and what we have here, this is the stator and this one is the rotor. So, the stator has got conductors. So, we have the stator conductors. So, we are taking a cross section here. So, we have the stator conductors and the conductors are distributed. So, let us say this is phase A. Now, when we call this to be phase A, the opposite of this has to be A prime. So, the phase A is spread over 60-degree here and 60-degree here. So, this is A prime. Phase B is shifted from phase A by 120. So, this is phase B, B and B prime, and we have phase C which is C here and C prime. So, we have phase A, phase B and phase C. So, we are taking a cross section here. So, this is a cross sectional view. So, we have a cross sectional view. So, and the rotor has got magnet, and the rotor magnet is of the following shape. The rotor has got permanent magnet, which is a core magnet, which is placed like this side and placed like this on the other side. So, we have two sets of magnet, and this magnet is creating a south pole and this magnet is creating a north pole here. So, we have a two pole structure, and if this is a south pole, this has to be north pole. If this is a north pole, we have a south pole below this. So, the rotor has got two pole structure. We have a south pole and we have a north pole, and the rotor is rotating let us say in anti-clockwise direction, maybe say in the clockwise direction. So, say that the rotor is rotating in the clockwise direction, which is this direction. This is omega m, speed of the rotor. So, if we see, we can plot here the induced DMF in the stator windings. We have the windings A, B and C. We can plot the induced DMF in the stator windings. So, what we can plot here, we will plot here induced DMF in phase A, induced DMF in phase B and induced DMF in phase C. So, this is a 0 in this case, and we will be plotting against the angle of rotation. So, these are the 60-degree intervals that we have. This is 180-degree, and this is 360-degree. So, what we see here, when it is rotating in the clockwise direction, we have the north pole which is here, this is the north pole, and we have a south pole which is here. So, the north pole is entering under the phase A. So, this is the north pole, beginning of the north pole. So, this is entering under phase A. So, the phase A induced DMF will gradually increase. We assume that south pole will give rise to, let us say, a negative induced DMF, and the north pole, when it comes under the phase, it gives rise to a positive induced DMF. So, in this case, the induced DMF will be changing from negative to positive over 60-degree interval. So, on after 60-degree, whole of north pole is under phase A. After 60-degree, south pole will be completely out, because the phase spread here is only 60-degree. This angle is 60-degree here. So, after 60-degree, the north pole is completely under phase A. So, this is what we have here, and then the north pole spreads for 180-degree, 180 minus 60 is 120. So, it remains constant for 120, and then it again decreases over 60-degree and remain constant for another 120. So, the waveform that we get here is something like a trapezoid. This is phase A, and hence we call this to be a trapezoidally excited or trapezoidal permanent magnet AC motor. Similarly, if we see phase B is shifted from phase A by 120. This is the beginning of phase B here. This is the starting of phase B. So, phase B starting is shifted from phase A by 120-degree. So, the phase A will have the maximum value will be somewhere here, phase B, and this is how the waveform of phase B will look like. Phase C is shifted from phase B by again 120. So, phase C will be, the positive will be starting from this point, and then if we plot the waveform, it will be somewhat like this. So, phase C is also a trapezoidal signal which is spread over 120-degree interval. So, these are the induced DMF of phase A, phase B and phase C. Now, when we have the 3-phase stator, the rotor is rotating, we have to inject current into the stator, so that the torque ripple is minimized. The induced DMFs are trapezoidal signal, the trapezoidal signal with a duration of 120 and 120 in the negative, and the transition occurs over 60-degree. So, we will now discuss about the current which has to be injected into the phase A, phase B and phase C, so that the torque ripple is minimized. So, the relevant calculation for current and torque will take up in the following lecture.